And Calum, when you're ready, please go ahead and give us your presentation.
Yep, excellent. All right, so I'm Calum Gordon. I'm a PhD student at the Victoria University of Wellington in New Zealand. And today I'm going to be talking about energy transfer from inorganic donors to organic acceptors for luminescent solar concentrator applications. And so just to actually start the slideshow. Cool, sorry, yeah, there we go. And so just to sort of set the scene, what are luminescent solar concentrators? Effectively, what they are is a sheet of glass or plastic with a light harvesting material within them. And when sunlight comes down to the surface of luminescent solar concentrators, this light harvesting material will absorb the light and then re-emit the light. And the re-emitted light by total internal reflection is waveguided to the edges. So effectively, what you're causing there is, if you imagine a large surface area of this luminescent solar concentrator, all the light from that surface area ideally will get concentrated to the edges, and the edges will glow really bright, as you can sort of see in that right-hand side picture there. And the power of that is that you can just line the edges of your LSCs with solar panels and harvest all that light energy from that large surface area at the edges. The benefits of that being, rather than having like a roof covered in ugly looking, costly solar panels, you can replace it with luminescent solar concentrators, which are a lot more aesthetically pleasing and also cheaper. The main issue with LSCs at the moment is that they aren't commercially viable, mainly because of a reabsorption problem that occurs within them, where the light harvesting material, after emitting light out, will actually later down the line just reabsorb that light energy again. And so this kind of causes a sort of parasitic feedback loop where we're constantly running through emitting and reabsorbing light and going through all those processes, which really increases the chances of us actually losing that photon's energy. So we need to look for ways in which we can get around that. Also, just in general, typically luminescent solar concentrators, the light harvesting material within them is toxic, which obviously isn't ideal. And so these toxic materials, they suffer from that reabsorption problem, as I described. You can begin to get around this by moving to a non-toxic system, obviously. However, they generally perform worse in terms of their emissive properties. Generally, they'll absorb light, but they won't re-emit it. And they'll also still suffer from that reabsorption problem. And so what we look to do in our group is actually, in our case, take a non-toxic nanocrystal, an inorganic material, and functionalize it with a emissive organic material. And what this allows us to form is actually a donor acceptor system where we're getting energy transfer from the non-toxic nanocrystals into the emissive dye material. And what this actually means is we've now got a non-toxic system that is emissive and actually doesn't suffer from reabsorption, ideally, because we've actually redshifted the energy of the photon in such a way that it can't be reabsorbed by the primary light harvesting material, that non-toxic nanocrystal. So obviously we want to make sure that we optimize energy transfer, as in order for this to work, we need to be getting ideally uniform energy transfer from the non-toxic material into the organic dye acceptor. So the candidate we've chosen as a good non-toxic donor material is indium phosphide shelled with zinc sulfide. So effectively, the indium phosphide core acts as the material which will actually perform the energy transfer. And the shell overcoating it, the zinc sulfide, is just to help passivate the surface of the indium phosphide, just basically to make it better at transferring energy over. Now, the trade-off with that is that generally the more we shell the indium phosphide, the better it becomes at transferring energy, but also the larger the distance we have between our donor and acceptor. And the energy transfer that takes place is a distance-dependent process, which means that if we've got too large of a shell, then we're going to trade off and have worse energy transfer. So in terms of optimizing energy transfer, there's a bit of things we can do there in terms of controlling shell size. So that's something we're interested in looking at. So we've made some of these shelled systems in the lab, and so we'll just go through some of the characterization of them. On the left-hand side, we have indium phosphide shelled with zinc sulfide, a thinner shell, and on the right-hand side, the same sort of system, but with a thicker shell. And so this is just the STEM images of them, along with their size distributions. We've also performed energy dispersive X-ray spectroscopy on these systems, which confirm the presence of indium, sulfur, phosphorus, and zinc, which is suggestive that we've got indium phosphide shelled with zinc sulfide. And in particular, when we compare the EDS data of these two systems, we'll see that we've actually got a larger zinc to indium ratio on the right-hand side, suggesting that we've got a larger shell on there. Now, just for some photophysical characterization, this is just the excitation and emission spectra of both of these systems. So they're both quite similar. Their exciton peak is at about 420 nanometers, and their emission peak is about 480 nanometers. You wouldn't expect much of a change here, given that the only thing we're really changing is the size of the shell. So now we actually come to the donor acceptor characterization, where we functionalize these donor systems with an organic acceptor. In this case, we've opted for rhodamine B, as from the literature, it's been shown to be a really promising candidate for energy transfer for these systems in particular, and also just because it's got good spectral overlap with our donor. So just to note, for good energy transfer, you want your donor's emission to overlap reasonably well with your acceptor's absorption, allowing for a sort of window for energy transfer, as you can see on the right-hand side figure there in that sort of green overlap area. So in terms of actually characterizing energy transfer, we perform that by doing a quenching analysis of the donor. And so on the left-hand side here, what we have is just an emission quench analysis where, as we progressively, if you can see my mouse there, hopefully, can you see my mouse? Yep. As we progressively add more acceptor, you can see the emission of the donor is being quenched. Now, the reason for that is rather than emit energy out, it's non-radiatively transferring the energy over to the organic acceptor, which is indicating that we've got energy transfer. A similar analysis was performed by lifetimes. Now, if you're not familiar with lifetimes, effectively it tells you how long your donor's emission, how long the excited state of your donor is before it emits its photon back out. And so for the donor by itself, you see we have quite a long-lived lifetime here, but in the presence of the acceptor, we've got a short-lived lifetime. And that's because all the long-lived excited states of our donor are now no longer having the opportunity to emit, because it's competing with the process of transferring energy over into the acceptor. Then we have a Stern-Volmer analysis where we compare the fluorescence intensity of our donor to the fluorescence intensity of our donor in the presence of differing concentrations of our acceptor. Don't want us to worry too much about this one, but just identify that this is a y equals mx plus c relationship in which we can extract KSV from the gradient of this graph here, use this KSV value to go and calculate our KQ value. And this is the important one I want us to be looking at, as this is our quenching constant. And ideally, a large quenching constant will actually tell us if the interaction between our donor and acceptor is static or dynamic. And so we'll look to that in the next slide. But first of all, I just want to summarize some of the data we have currently. So for the two donor systems that we made, I just note that for the previous data that I showed with the quenching and the Stern-Volmer, that was just for the indium phosphide system with a thinner shell on it, but we've also performed the same data on the larger shell. I just didn't want to show all of those figures because they do look quite similar. So yeah, just to summarize some of this data, we've got our size distribution here, the ratio of zinc to indium in terms of that energy dispersive X-ray analysis, the photoluminescent quantum yield of both of these systems. So effectively, when light gets absorbed by these donors, how much comes out again? So 40%, 42%, and the full width half maximum of the emission of both of our donors. And so what I really want us to be taking away from that is that the values here are variant. And what that's suggestive of is that we do have different systems where one has a larger shell and one has a thinner shell. Then in terms of the actual donor-acceptor characterization, this is just the ratio of acceptor required to fully quench the system. And then on the right-hand side here, we have our quenching constants. And you'll see that they're to, I think, 10 to the 13. Yep, 10 to the 13. And so what that's suggestive of is a static interaction between our donor and acceptor. So with that all aside, we've now got that system where it appears that the donor and the acceptor is attached, or well, not attached, but rather statically interacting. And we've got energy transfer. It's time to actually quantify how much energy transfer we're getting. Now, the energy transfer taking place here is known to be Forster resonance energy transfer. And so this is the equation for our energy transfer on the left-hand side here. And what I mainly want you to be taking away from that is that it's inversely proportional to the distance between our donor and acceptor. Yeah, so the donor-acceptor pair distance. So basically, the closer our donor and acceptor are to each other, the better the energy transfer becomes. Now, this R0 value is just our Forster distance, and try not to be too scared off by the equations, but basically, this is just proportional to how good your donor system is in terms of its photoluminescent quantum yield, and how good the spectral overlap is between the fluorescence of your donor and the absorption of your acceptor. So the actual quantified energy transfer analysis can be extracted by comparing the ratio of the fluorescence of your donor and acceptor against the fluorescence of the donor by itself. And the same can be done with the lifetimes as we did before. And so these actually come out with values that line up fairly nicely with each other, basically greater than 70% for both of these systems, which is really quite good. Now, using these energy transfer values, we can actually work backwards in our Fred equation here and actually solve for the donor-acceptor distance, which we've done on the right-hand side of the table there. So that's the actual distances between the donor and acceptor. Cool. So to just conclude this part of the talk and talk about the future directions in terms of these donor-acceptor systems, effectively we've been able to successfully make these indium phosphide systems with a zinc sulfide shell functionalized with rhodamine B to give us a donor-acceptor system that's capable of performing energy transfer that's greater than 70%, which makes them good candidates for luminescent solar concentrators. In the future, we want a bit more of an in-depth investigation into how shell size will actually affect these systems, as increasing shell size can improve thermal stability. It can improve the ability to harvest light. But of course, there is that issue of potentially trading off with worse energy transfer. So a multitude of factors that we want to kind of investigate there. It would also be really cool to model the ligand interaction at the surface of the nanocrystal. So perhaps a computational study where we actually look at how the organic acceptor is interacting with our nanocrystal. Maybe we'll be able to get insight into how we can maybe even better design new acceptor systems that sit more nicely and closely to the nanocrystal, providing even better energy transfer. Cool. So for the next part of the talk, I want to talk a bit more explicitly about luminescent solar concentrators themselves and the events that take place in terms of all the potential sort of fates that can happen to a photon during the concentration process where we ideally collect it at the edge. So first of all, the photon gets sent to the luminescent solar concentrator, and from here it can get reflected off the surface of the substrate, or it can be absorbed by the substrate. And in both of these cases, these aren't ideal because we lose that photon's energy and we just have to cycle back, get another photon sent in, and hope that one works out better. But provided we don't go through these loss mechanisms, the photon is ideally absorbed by the light harvesting material inside of the concentrator. Now from here, it can just non-radiatively decay. We can just lose the energy in that manner. But provided that that doesn't happen, the photon will be re-emitted. Now, as the photon is now re-emitted in the concentrator, once again, it can get absorbed by the substrate. It can potentially get lost out of what we call the escape cone, where the angle of the photon exceeds the critical angle between the substrate and the air interface. And then we can, of course, have that reabsorption issue, the one I briefly talked about before, where we get that nasty feedback loop, where we reabsorb the photon, then it has to go through these cycles again, where we have these loss mechanisms getting run again and again and again, really perpetuating the chances of us losing that photon's energy, which is not ideal. Now, provided that neither of those cases happen, the photon will be, or any of those cases happen, the photon will be waveguided to the edge, where it will then be collected by a photovoltaic cell, which is, of course, our ideal case scenario. Now, the reason why I wanted to talk about luminescent solar concentrators more explicitly, and all the fates of the photons that are the fates that can happen to a photon in a luminescent solar concentrator, is because in this flowchart here, all of these blocks actually represent discrete blocks of code that altogether form a simulation or a model for a luminescent solar concentrator, which I think is really cool. And so on the right-hand side there, we actually have a simulated luminescent solar concentrator by Zhang and co-authors, where you can actually see the concentrator actually simulated itself, and all of those squiggly lines in there are actually the photons, and what the fate of the photons are if they escape the edges, if they get absorbed by the substrate, and also what wavelengths are. So I thought that was kind of just a cool picture. But yeah, sorry. So the real power of having all these discrete blocks of code that form one model is we can seamlessly integrate our own blocks of code to fit our purposes. And so what I'm of course talking about is integrating code that handles energy transfer, which means we'll be able to actually simulate luminescent solar concentrators for the hybrid materials that we've made in the lab, which is something we are now looking at doing. And so, of course, this is just what happens when we get energy transfer in a luminescent solar concentrator. And so just to conclude and talk about the future directions more on the luminescent solar concentrator side of things, we've got those donor acceptor systems. And in terms of the future directions of the concentrators, we want to simulate those donor acceptor systems and determine the optimal concentrations necessary to get the best device performance. And then, of course, actually make the devices in the lab and test their performance and properties. So I'd just like to acknowledge my supervisor, Nate Davis, and the Davis group. That's all of us in the left-hand side picture there. And I'm happy to answer any of your questions. Thank you.
Excellent. Thank you, Calum. Very interesting talk. So we'll open it up to questions from the audience. If anyone would like to ask a question, please just unmute your microphone and go ahead, please. I see we have a question in the chat, actually. Laszlo Fraser says, what proportion of the solar spectrum can indium phosphide quantum dots absorb if you tune them as red as possible? So what proportion of the solar spectrum can you absorb?
You can get really, really red with them. You can get pretty much all the way absorbing almost all of the visible spectrum. I don't think you can get as much in the near-infrared from there unless you dope them with copper. The problem with that being is that it becomes a bit more, well, I suppose it's not, yeah, I have to think about that, but at present, we just don't have a good acceptor candidate that I can think of that would transfer that low energy into an even lower energy acceptor, if that makes sense. But you can capture pretty much all of the visible spectrum, I think. Yeah.
Were there any other questions from the audience? If not, I might just ask quickly, so how does the performance compare to other systems in the literature? So you said, I think a 70% rate of efficiency?
Energy transfer,
yeah. So how does that compare?
Yep, so for these systems in particular, that's pretty much on par with the literature. No one's been able to make To my knowledge, I haven't seen anything for these systems in particular that reach 80%. That'd be quite cool to be like, you know, try and break that barrier. But yeah, so it's about on par with the literature.
Because it seems like it would be quite challenging to trade off the initial absorption of trying to capture the photon for the first time, but then not reabsorb it, right? And so there'd be a delicate balance there. Is that the case based on your understanding?
Yep. Sorry, can you repeat the question?
So you have these two competing processes of you need to absorb the photon in the first instance, and then once you re-emit it, you want to not reabsorb it again. So I guess there would be this delicate balance of trading trading off all of the different properties that go into those effects to get an optimal system.
Exactly, and that's just part of the optimization process. Yeah. So you're quite right. Like if you tune the quantum dots, or sorry, the nanocrystals such that they overlap with the dye a bit better, then you can get better energy transfer. But what's the point if it's too close and it can reabsorb? With these systems, the Stokes shift is about, I think, 110 nanometers, which is really good in terms of mitigating reabsorption and still having high energy transfer. So I'm quite happy with this candidate at the moment, but it's definitely something we do want to explore as well, just playing around with making slightly redder shifted nanocrystals to get better energy transfer, etc. But yeah, no, you're dead right.
Yeah, absolutely. So thank you very much, Calum, for the interesting talk.
Yeah. Should I answer this last question?
Yeah, just really quickly. Yeah.
Yep. Sorry. Yeah. So to measure the distance between the donor and acceptor, it's just by that FRET equation before. So just get that. Sorry. So since we know the energy transfer of the system, we can solve for E here. We also know the Forster distance based on spectral overlap and the PLQE of the donor. And from there, you can just solve for R. So that's just that, how you do that. Cool.
Excellent. So everyone, please join me in thanking Calum one more time for a very interesting presentation.